solenoid. Solenoid means, you see, insulated cylinder, cylindrical insulator, and you just go on circulating the wire over it. Means it's like a coil which is having many turns. This would be known as solenoid, and every current carrying coil behaves as a magnet, and here you are having so many coils. Obviously, when the current will pass through solenoid, it's going to behave like a magnet. The only difference and superiority of solenoid is going to be that it produces uniform magnetic field inside it. This is a solenoid. Suppose the length is L and there are n turns in the total solenoid, then this is known as turn density. Total number of turns upon the total length of this solenoid, this you would call as turn density. For finding the magnetic field, you see, I have chosen a particular point inside the magnetic field, suppose here, then we'll consider the points. This one, this is suppose angle is given phi 1. For the other side, because the angle is always taken from anti-clockwise sense, this way you will consider the angle. So, for the other end, this angle is going to be phi 2. We'll say that if two ends of the solenoid are making angle phi 1, phi 2, then magnetic field at that very point is going to be given by this μ₀ Ni/2 cos phi 1 minus cos phi 2. If you consider the solenoid to be very long, you see, then in that case what's going to be here, this angle will become very small if this length is increased very long. Similarly, this angle is also going to become 180 degree. That means for a very long solenoid, you are going to have the angle 0 and 180 degree. Cos phi 1, this will be plus 1. And cos phi 2, this is going to be minus 1. If you put the value plus 1 minus 1, it is plus 2. This plus 2 will be cancelled by this 2, and ultimately in that case you are going to get the magnetic field within the solenoid, inside the solenoid, given by μ₀ Ni. How interesting it is. You see, you are not finding the location or the angular coordinates you are not going to have over here. So, you could say that the field is uniform throughout the solenoid. That is why I pointed out earlier, it is a better choice for producing uniform magnetic field. But if you consider point at one end, you see, for one end this angle is going to be 90 degree and the other side this is going to be 0 degree. In that case, you see, this is going to be μ₀ Ni/2. Cos 0, this is one angle will be 90 and one angle will be 0. Then this will be cos 90 will be equal to 0, and this is going to be μ₀ Ni/2. This again is one memorable result, that field at the end is exactly half of the value in the middle. Whatever the field is produced in the middle, exactly half of this you obtain at the end of the solenoid. That's shown here, but this is not a drastic change. This takes place very slowly or gradually, you might say. Now, what is toroid? Toroid is a solenoid bent in the form of a circle. As I have shown over here, it's simply a circular coil with solenoid adjusted over it. And this is very interesting. You see, you consider this solenoid like this. If you consider the point outside, here solenoid this way, wire has been circulated around it, current is going vertically upward, then the other side it is going vertically downward. That means overall no current is there. One is plus I, then other is minus I. The sum of the two is going to be 0. That means if you consider the point outside, no current will be enclosed by this loop on the basis of Ampere's law. There will be no magnetic field at this point. Similarly, if you consider the point here, then again here at this point, again no current is going to be enclosed by it, magnetic field will be 0. Only field will be produced within this solenoid throughout, and this is very interesting. It is said to be a magnet without any pole. Toroid will have the magnetic field uniform throughout inside, but there will be no clarification or bifurcation of the poles. That's why it is said that toroid, every toroid is a magnet without any pole. There is one basic difference between solenoid and magnet. Magnets have their magnetic strength is stronger at the poles and so very weak in the middle. Whereas for the current carrying solenoid, you find the magnetic field throughout uniform, rather it is little less at the end point.